Okay, got a couple questions here from chapter 14, number 16 here. And so this one has, I'll just kind of put the book in here, but this has this U-shaped device here. And it says mercury is poured into the U-shaped device as shown. And then later on, we pour some more water in here. And the water then, of course, pushes this mercury down, which lifts that up. And so the question here, at least question A, it says determine the length of the water column. And A is not anything really fancy here. We just have this tube here. Well, it's part of a U-shaped tube, so I'll make my U-shaped tube here. But the mercury was sitting at about this line here. And then as we poured the water in on this side, so here comes some water, the weight of that water, so I'll just make the upper part of the water here, goes to here. And so this is all water, whereas the mercury then gets pushed up to here. And they say in the problem that the cross-sectional area of this is A2, and they even give us a number here at 5.00 square centimeters. So the key to it says 100 grams. Now water has a density, so density of water is 1 gram for every cubic centimeter. That's actually the same as 1,000 kilograms per cubic meter. And so there's times that one of these is better. And I think in this case, this time this is better, although when we do calculations, usually this one is better. But because they said 100 grams, we know that the volume that we poured in is 100 cubic centimeters of water. And we also know the volume of a cylinder would be the area, cross-sectional area of the cylinder, that's this part, times its height. Let's call it the height of the water. And since they gave us this cross-sectional area as 5 square centimeters, we can then easily enough get the height. And so take the 5, divide it by 100, that's 20, and then centimeters cubed, and canceling with a square leaves us with 20 centimeters. And so this total height here is 20 centimeters. So that's the height of the column of water. That's, again, probably the easier part of this question. Now, the harder part of this question here, and where it really comes in, it's maybe a Bernoulli, maybe more of an Archimedes, depending on how you want to look at this. Let's see, I'm just kind of looking at what section it is. Yeah, it's under the section that says pressure varies with depth. So haven't really gotten to the Archimedes or the buoyant force yet. But I'll go ahead and just write out Bernoulli's equation. It's a little more all-encompassing, even though we don't need it. It just says that on one side over here, on this side of the tube, the pressure, I'm just making it hard. I'll just do like they show. They say the pressure, and so this is the atmosphere. So let's call this P naught, and so P naught plus then rho G, and I'll just call it H here for a moment. How far deep you go then is the pressure. So this part is the increase in pressure as we'd go down in the mercury or as we'd go down in the water. And then, of course, the P naught is from the atmosphere. And this is really the key to the problem. If you draw a horizontal line across here, and maybe even maybe a vertical line down here at the bottom, right here, when things stop moving, and that's the key, when things stop moving, so you pour some water in here, and then, of course, that makes the mercury shift over to here. But not while it's shifting, but after it's done shifting, right here, you know then that the pressure pushing to I guess, to the right is equal to the pressure pushing to the left. And that means the pressure going all the way up, which is in this case caused by the mercury and the atmosphere, must be the same as going all the way up this side, which is caused by the mercury, the water, and the atmosphere. So that's why they're balanced. And in fact, you don't have to go all the way down here to the bottom, and that's why I wanted to draw this line here, because from here up, either up to the left or up to the right, we're going through mercury. And so it would be the same equation. So I can conclude that then the pressures at these points are the same. Of course, I do that from this bottom one. So I guess we kind of really have to talk about the bottom one. That the fact that the fluid isn't moving tells me these pressures are equal. And then the fact that it's both mercury going up would be the same decrease as we go up in pressure, and so we would be at the same pressure here. Now, going further up, here's where things begin to change, because going up, say, just 1 centimeter in water versus 1 centimeter in mercury, this would not be the same, because the densities is different over here on the left, going up 1 centimeter with mercury, going up 1 centimeter versus the water. So another vertical line here would not be at the same pressure. So what I'm going to do then is ignore kind of the bottom part now of this U-shaped cylinder, and just know that the pressures are the same here. And the way I would calculate this pressure would be to say it's caused by the atmospheric pressure, so from here, and then this pressure. And so that would be the density of the mercury times G times this height. Now, they label this as H. They don't give a symbol here, but in the solutions, they call that H2. So let me put H plus H2. And so that's this increase in pressure. And the reason that's important, like I said, to go all the way down to here, because there's no other horizontal line that would have the same pressure other than here, or any other horizontal line below that. And so I know that pressure, which is caused by this little equation, has got to be the same as the pressure over here, which would be caused by this water column as well as the atmospheric pressure. So there's the atmospheric pressure. Then we would have a density, and I'll put a W here for water. We would have a G, and then we would have this whole length here, this whole height, which we called W or H sub W, but I'll just put it as a number for right now because it's 20 centimeters. And since pressure is usually calculated in pascals, and pascals are in newtons, and newtons have meters buried inside of it, then I'm going to change this height to meters here. Okay, now continuing on, we can see that it doesn't really matter what the atmospheric pressure, it could be high or low, but it's the same on both sides, so that cancels off. And of course, in this question, we are asked here, what distance h, so where h, does the mercury go up? So we're after this h, and as it stands right now, we know everything but these two. That is, the density is given, and I suppose the units aren't too crucial because they'll cancel off on both sides. But again, as I said, pressure is usually measured in pascals, and pascals has got newtons, square meters in it. So let me put for the density 13,600 kilograms per cubic meter. I noticed in the book they gave it in the smaller units of grams per cubic centimeter. And like I said, in this case we can get and just cancel them off. But just to be a little more formal and consistent, I'll put the units that would lead it into pascals, because the G is the 9.8 meters per second squared. And then so here is my height. And then, of course, if I put in the density of the water, which is the 1,000 kilograms per cubic meter, again, same kind of logic here, using the units that would give me pascals, but they're on both sides, so it's really not that crucial for this problem, but some problems it is. And then here's the 9.8. In fact, those units, and even putting the number doesn't matter because it's going to cancel on both sides. And I get 0.2 meters. But again, if I, just kind of pause right here, you'll see that I have an equation with two unknowns. So I need another piece of information, and that other piece of information is a volume piece. That is, drawing this, or coming back to this picture with this line across here, and labeling over here as H2, the mercury that left here went up here. So you might call this a conservation of volume, if you will. That what left here shows up here. So over here, the volume would be A1, I didn't put it over here, but this cross-sectional area times how high it went should be then the same as cross-sectional area 2 times this H2. And so there's another equation that has an H and an H2 in it. So between this equation, 1, and this equation, 2, we have two equations, two unknowns. And why don't I then use this one to solve for H2? This would then say cross-sectional area 1, which they say is 10 square centimeters, divided by cross-sectional area 2, which they say, is that 5? Then times this H, of course, is then equal to H2. And so 5 divided by 10 is 2. So this would be 2H for H2. All right, so now let me use that. And so taking equation number 1 and continuing to work with it, in fact, maybe I'll just cancel off units here, and then the 1,000 goes into here, so this would be 13.6. Then I would have an H plus, and then right here at the H2 would be 2H, then equals, and I already divided by 1,000, and then this would be the 0.20 meters. And so this together is 3H, so H would equal, with my calculator here, and so over here I have a 0.2, and we'll divide that by 13.6, and divide that by 3, and I get 0.0049 meters, or putting things back to centimeters, since that's how they were given. I get just, 0.49, that doesn't look like a 4, 0.49 centimeters. Yay.